here's our bell work. Is this graph a function? Well, to figure this out, all I'm gonna do is use the vertical line test right here. So here's my vertical line, I'm gonna scan it. And again, all I'm looking for is if this line ever crosses this green line more than once at the same time. Because if it does, then it's not a function. And see, pretty much right here, you can see that it crosses here and here. I mean, it did before that, but this kind of emphasizes it. So this one right here, not a function. Okay, here's our two objectives for the day. I can determine the independent and dependent variable in a relationship. And also I can determine when a function or equation is linear or nonlinear. Take a minute and copy that down, please. So let's start with our first objective. We got independent and dependent variables, okay? So in any situation, at least when we're looking at two different types of quantities here, it may take some time to look at this, and you may have to reread it a few times and even think about which one would be independent or dependent, but it really just comes down to either one of the two questions. And the one that usually seems to make most sense with most students is just ask yourself which one of these depends on the other one. So which one is changing because the other one is changing, okay? Because if it's independent, it just changes on its own. But if it's dependent, it will change because of something else, okay? See, and then once you know that, then you know which one's dependent, which one's independent. Now, the thing about that is, when you look at the dependent variable, that is the y values. And once you know which one is independent, you know that represents your x values, okay? So yeah, dependent, y values, independent, x values. See that? Okay, and you can think about it like this too. Like if you're walking, and maybe you're comparing like distance to time. Distance and time like this, right? Let's say you're walking again. So if you're walking and we're comparing distance with time, again, you can think about, well, if you're walking, which of these would change because of the other one? Which one depends on the other one? Well, time by itself would just go no matter what. But distance, the distance that you walked will depend on how much time that you have walked. So in this case, would say that distance would be dependent, and then time here would be independent, okay? Like this. In fact, usually when we see time, it is almost always considered independent, okay? So here's a few situations for us. Each of the following situations represents a functional relationship between two quantities. All we got to do is determine which one's dependent and independent, okay? So if it's dependent, then I'll say that I'll just use a D next to it, and then if it's independent, I'll just put an I next to that. We have to identify the two values that we're comparing, okay? So in this first one, it says, in warm climates, the average amount of electricity used rises as the daily average temperature increases and falls as the daily average temperature decreases, okay? So here we can see the two things that we're comparing. And again, this may take several readings or rereadings in order to actually understand what's going on here, but expect that, okay? Because these do take some time when we're just getting used to them. Right here, we're comparing, I guess you'd say, even amount of electricity used compared to temperature, right? And so if you were to compare those, which of those depends on the other? Now, we're looking at electricity used, which generally means that you're looking at either warming your house or cooling your house, okay? So if that were the case, then right here would say the electricity used will depend. So I'm going to put a D there. It's going to depend on the temperature, which would then be independent, okay? Electricity used depends on whatever the temperature is on the outside of the house, okay? So that's dependent and independent, which means that if we started to make a table or looked at the values, we would say that the temperature would be your X values, and then the electricity would be your Y values, okay? Now the next one, the number of calories you burn increases as the number of minutes that you walk increases. So two things we're comparing on here. Looks like calories burned, and then minutes that you walk, okay? So we're comparing these things, and again, you can just think to yourself, which of these is going to depend on the other one? Or you can ask yourself, it's pretty much the same question, but which of these is changing because of the other one? And right here I can see that the calories burned will depend, it's going to depend on the minutes that you walk. So calories burned is dependent, minutes walked is independent, okay? And again, that means that if we were to actually represent this situation in a table or a graph or an equation, X is minutes walked and Y would be calories burned. The next one says the air pressure inside a tire increases with the temperature. So we can see here that we're looking at the pressure inside a tire, and we're comparing that with temperature, okay? So which of these depends on the other one? So it even says, if you read into this, again, you may have to reread this several times before you fully understand this, but the pressure inside the tire increases with the temperature. And another way to word this is that the pressure inside the tire increases because of the temperature. So that means that the pressure inside the tire would be considered dependent, while the temperature on the outside we would consider that to be independent, okay? Next up, we got the amount of rain decreases. As the amount of rain decreases, so does the water level of the river. So right here we're looking at the amount of rain. That's one thing that we're comparing with the water level of the river, okay? So, and again, you can think about this in a different way. You could start with which one depends on the other, which one is changing because of the other one. But we know the two things that we're comparing. On this one, you could even ask yourself, which one is just going to happen no matter what? Well, on this one, you could say that the amount of rain is going to it's just going to rain, okay? But the water level of the river here is going to change because of the rain, okay? That means that the water level of the river would be dependent, and the amount of rain here would be considered independent, okay? Because if there's no rain, no river, okay? So next up, the total number of jars of pickles that a factory can produce depends on the number of pickles they receive. So the two things we're comparing on this one, number of jars of pickles, and then pickles received, right? And it even says on this one, it even used that word depends. And so this one actually kind of gave us the answer. The jars of pickles, of course, will depend on how many pickles that are in the factory, right? If they don't have very many pickles in the factory received, then of course you can't make that many jars of pickles. You could have a bunch of jars empty sitting around, but you couldn't make them jars of pickles until you get more pickles in, okay? So there's a lot of thought that goes into this, which you can see. And let's look at this last one here. The weight of the box increases as the number of books placed inside the box increases, okay? So the two things we got is the weight of the box, and then the number of books here we would say being put into the box, right? So this one, again, which one will change because of the other one? And it kind of said, again, even this type of wording reveals which one's dependent and independent. But the weight of the box increases as the number of books placed inside the box increases. So the weight of the box is changing because of the number of books, which means that the weight of the box here would be considered dependent, and the number of books would be considered independent, okay? Now again, the reason why we do this is so that when we see future problems that have words in them like this, and then they say make a table or a graph, we don't have to wonder to ourselves which one is X and which one's Y, because if we can just know which one's dependent and independent, then we can make those out ourselves, okay? Now, I believe in science in 7th grade, maybe even by 8th grade by this time, they have talked about independent and dependent variables. So this is pretty much the same thing, just, of course, in a math context. So next one, the library charges a late return fee for any book that is returned after the due date, plus the charges added per day that a book is returned late. The table below shows the total fee for a book returned any number of days late. And this one, see here, they even told us which one's X and Y. So we can see the number of days late, that's our X values, because they show us the X right there. And then the total fee there, that's going to be our Y values, okay? That means that right there, the total fee, that depends on the number of days late. Independent, okay? Dependent and independent. So identify the constant rate of change for this situation. So I believe that you've seen this before a little bit in 7th grade, finding a rate of change for a situation like this. Another way to say this, though, rate of change, which I believe we've said before, this is what we call the slope, okay? So rate of change is slope. Okay, so when they're saying find the constant rate of change, you're just finding the slope. Now, the nice thing about this is that they've pretty much given us 4 ordered pairs in this table. Remember, for ordered pairs, you have X values on the left and then Y values on the right. So that's 8, I'm going to say that's 8.5 or 5.0. That's an ordered pair. And then 12 and 5.8, that's also an ordered pair, okay? Now, we already know how to find slope from ordered pairs, so I'm going to show that again with slope formula, okay? Remembering that X values go in the denominator, Y values in the numerator. That's for both ordered pairs, okay? So in my first ordered pair, the X value is 8, so I put that in the denominator, and the Y value is 5. You could say 5.0 if you like, but it's not going to change the value. That would be in the numerator. And then for the second ordered pair, by the way, there were 2 other ordered pairs that you could have used. Thank you. There were 2 other ordered pairs you could have used on that, but we only need one. One other one, I should say. Okay, so we only need these 2. So this means that if you would use this ordered pair, you should get the same exact slope, okay? Let's see, we got 8, 5, and then I said would use a 12 and 5.8, 5.80. Okay, so again, this is just something that we plug directly into the calculator, and then it will give us the slope, okay? So we got 5 minus 0.8, and that, I'm using the fraction button, 8 minus 12 there. Oh, I got 0.2, okay? 0.2, you could say 0.20. Since it's a rate of change, we can put labels on this. This is dollars per, I guess, day late. On this one. So identify the constant rate of change. It's 20 cents per day. Day late, if you want to be more specific. Now that's one way to find the slope on this, right? The rate of change. Like I said, there's another way to do this, and that is to see the changes between the X and Y values here. So here's what I mean. So to get from 5 to 5.8, and I usually start with my Y values, I'd say how much change occurred right there? Well, you went from $5 to $5.8. That would be 0.8, which is 80 cents. And then how many days went by after that? You went up 4 days. See this? You can even label those. 4 days, 80 cents, right? Well, the rate of change is just a ratio between those 2 values. As long as you know which one's independent and dependent. So in slope, when you look at slope, it's always your change in the independence. In fact, I'll use I. It's change in dependence, change in dependence divided by independence. So if you're looking for those labels, or if they even give you the labels, then you know which is which, okay? Beyond this one, that's a ratio or a fraction Well, we just saw there that the change in the dependent variable was 80 cents, so 0.80, and then it took 4 days. And when you divide these two, you're going to get the same 20 cents per day. And you could even label those in the fraction. Okay, 80 cents per day. Well, what about those other points? This means that you could use the other ordered pairs to find the slope there, right? See right here, 5.80 to 6, that would be an increase of 20 cents. And right here, 12 to 13, that was 1 day. Well, that's pretty much the same slope that we just found here, just simplified, right? And then we should get the same thing on this one. From $6 to $8.40, that increased $2.40. But now it increased by 12 days. So if you take $2.40 and divide it by 12 days, once again, you get that same 20 cents late, 20 cents per day late, okay? So going through these tables, and this is just kind of to find the rate of change. We know there's some rate of change here. I guess they didn't really ask if it was linear or not. But in the future, if they ask us if it is linear or not, this is the method we're going to be using right here. Because you could just say, I'm going to use the slope formula throughout, but you can find it pretty quick using this type of method here, okay? Then it says identify the initial value for this situation. Remember, we have our y-intercept formula, right? And that's what initial value is. It's a y-intercept. So that's what I'm going to use. Remember, that's y minus m times x. Remember, m is slope, which we just found was 20 cents per day. So I'm just going to use the value there, 0.20. And then any of these ordered pairs will do, okay, from the table. Any of these will do. I tend to just use the top one here, 8.85. You could use any of these, though, and you'll get the same y-intercept. So in that ordered pair, the x value is 8, and then the y value is 5. You could say 5.0. If that helps you remember which or where that value came from. Thank you. Okay, and then at this point, all I'm going to do is plug this into the calculator. So let's see, 5 minus 0.20 times 8. Enter. And this tells me that the y-intercept here would have been $3.40, okay? Now, what does this represent, this $3.40? This represents whatever the initial fee was, right? Plus a charge is added per day. So it says library charges a late return fee. That's this late return fee. That's this $3.40 right there, okay? Now, why does that help us? Because when we want to write the equation, which is this third part, all we got to do is find the slope and y-intercept, just like we've seen before, right? We say y equals mx plus b, and we just found, well, we found the m first. I guess I made it green. That was 20 cents per day, and it's okay to use the decimal here because it's a word problem. And then, so that's our 0.20, and then remember it's kind of like this plus b value, which we found was $3.40. Okay, and this would be representative of the equation. And they even told us here, once again, that the x represents the time in days. That's independent. And then y is the total late fee, which is, there's dependent, okay? So we have to be able to write equations from a table like this, or pretty much a word problem. But then it says, what does the point 5.20 represent in the context of the situation? Well, the x value describes, in this case, we know the x value there is 9, right? So it's 9 something. And again, since we've already identified which of these is independent and dependent, x values are independent. Okay, we know that the x values are always going to be independent, so that'd be 9 days. You could say 9 days late if you'd like. And then the y values are the dependent variable, right? Which again, we've already found ourselves, but they were given to us dependent. There we go. And again, they were given to the table right here. That's the total fees, and that's just dollars. So this $5, this 5.20 would be $5.20. You could put fee on that, but I'm okay just saying $5.20. Okay. Now on the assignment for this one, they're just going to say they're not going to ask for a 9 or the 520. They're just going to say label these. Okay. And since we know which one's independent, that's always our x values. Dependent is always the y values. If you're not sure which of those it is, this one gave us those, right? In the table and also in the wording up here, and even right here when they asked for the equation. All right, this next one, you just got a new phone, you send an average of 24 texts per day, identify the constant rate of change for this situation. Now remember, constant rate of change, that's the slope, okay? And even the second question, what's the initial value right here? That's the y-intercept. Now, in this context, though, there's not a lot of calculation going on. They didn't give us any ordered pairs, no table, not even a graph for this one. But they didn't have to because up here at the top, see how it says 24 texts per day? So if you think about the two things that we're comparing on this problem, okay? You got a new phone, you're sending some kind of average of 24 texts per day, okay? So the two things we're comparing are texts and days, but the word per indicates that it's some kind of fraction, which means that you could have just written this as 24 texts per day like this one. You can even say 1 day if you'd like. But remember from that last slide, your dependent variable is always going to be in the numerator because that's your y values or change in y values, and your independent will always be the denominator. So this one actually gave us the dependent and independent variables right away. But also, since it's showing a comparison of these two values, that right there is the slope. Okay, so we can put this in right now. The rate of change, 24 texts per day. You could show that as a fraction if you'd like. And I believe on the assignment for this one, you just put 24. You don't have to write in text per day, but it's important that you understand that it is 24. Why is that important? Because this third part here, write the equation to model the situation, that's going to ask us to write the equation right there, right? And what two things do we need to write the equation? The slope and the y-intercept. Okay, so what's the y-intercept for this one? Again, they didn't give us any values, so we can't really use the formula. Again, you should be able to think about this one and ask yourself pretty much one simple question for this one. How many texts did they send? You could say before or when they got the phone. Because this would be how many texts did they start with. Now it's not asking how many texts they sent after day one. It's asking how many texts they sent before they started sending texts. And in this case, that would be 0 texts, okay? So that's the initial value on this one. On day 0, they send 0 text, which means that we could also write this as an ordered pair. 0 day, on day 0, they had sent 0 text. At the beginning of day 0. Now write the equation to model this situation, where x represents the number of days and y the total number of texts. Okay, well, this goes back to slope-intercept form. Y equals mx plus b. And again, I'm just kind of filling in the blanks right here. Some people are still only writing one value when they write these equations, but we need both values and the y and the x, okay? So we found the slope there is 24 texts per day. I think you have to put the 24, and then the initial value, the y-intercept, you could put plus 0. You could make that a phantom plus 0 if you'd like, but I'll keep the plus 0, okay? Now, what does the point mean in the context of the situation? Let's make up our own here because they didn't give us one. So I'm just going to make one up on this. Let's say what does the point let's see, that'd be 15,360 on this one, okay? So I'm just making that up as we go, but on this one, the x value, we know it's 15, and the y value is 360. We just need labels for these, right? But again, up here, we've already identified the independent and dependent variables. So if it gave us an x value that's 15, we can see here that the independent variable is the denominator in that fraction or the ratio, and so that would be 15 days. After 15 days, we would have the y value, which is the dependent variable. That'd be 360 texts. And hopefully this would make sense. Like if you had mixed those up, 15 texts in 360 days. No, they're sending 24 texts every day, so definitely not if you had switched these up with days and text. It should make sense that it's off, okay? Well, this brings us to the second objective, linear versus nonlinear. So a few things here. We're going to be comparing these on graphs. If you want to determine if something's linear on a graph, it's so easy. All you got to do is look. No calculations involved. You're just looking for a straight line on a graph. As soon as it's curved at all or like breaks and then goes in a different direction, then it's not linear anymore. Okay, so sometimes for nonlinear graphs, you can have a graph that kind of looks like this. It'll be straight, and then it kind of breaks the other way straight, like this. This is still not linear because it's not a straight line throughout, okay? So it just has to be one straight line if it's going to be considered linear. When we compare tables, all you're looking for is a constant rate of change, just like we did 2 problems ago at a library fee one, okay? So if you find that there's a constant rate of change, meaning the slope is the same for every set of points, then you know that you're dealing with a straight line, okay? But as soon as the rate of change is not the same between values, then you know that you're looking at a nonlinear relationship. And then we're going to look at equations, okay? For linear equations, you're just going to you either have no x in the equation or the x will just be by itself with some kind of coefficient, okay? The x, what I'm saying here is the x won't have an exponent, or it shouldn't be in that should say denominator there. And this one, for equations, the x cannot be in a denominator, okay? If it is in the denominator, we would know that it's nonlinear. If there's some kind of absolute value or root, I think some of you have seen this symbol before, a root like this, then it's automatically, if the x is in this type of thing, then it's considered nonlinear as well. Or if the x has some kind of exponent. So here's what I mean, is if you have an x like this, maybe even like a 3x, that would be considered linear until you see some kind of exponent like 4. Okay, now it's not linear anymore. Yeah, and that'd be like y equals here too. Or, so that's nonlinear, but let's say that you made the x in some kind of absolute value like this. Not linear. Okay, if I take that away again, it's linear now, but if I put the x in a square root like this, not linear anymore. Okay, so pretty much all of these are a visual check except maybe the tables. Okay, but when you're looking at a graph or when you're looking at an equation, you can tell pretty quick if your situation is linear or not. So let's make the table and the graph for this equation. Now, right off the bat here, I'm going to answer this last question, determine if the relationship is linear. Remember on that last one, if we said if the x is ever in some kind of absolute value like this, automatically, right away, you can say this thing is not linear. And we'll show that on the graph, and we'll show it in the table too, okay? So this one, notice that it's not even asking, it didn't tell us any x or y values to use. So I'm going to make up my own on this, okay? So I'm going to say, let's say x is -2, -1, 0, 1, and 2. Okay, so I'm kind of staying pretty close to 0 here. Now, if I go into this equation, y equals the absolute value of x. But right here in this first one, I'm saying, look, let's replace the x with -2 and see if what y value this gives me. Well, this would give me the y value. The absolute value of -2, again, how far away is -2 from 0? It's 2. So that gives me this ordered pair, 2, 2. And I'll do the same thing for y equals -1, right? Y is the absolute value of -1, which is y would then equal 1. So I got -1, 1. I'll do the same thing for 0. Y equals the absolute value of 0, which tells me then that y would be 0. Okay, so I get this ordered pair, 0, 0, that's right at the origin. What about y equals the absolute value of positive 1? Well, if this were the question, 1, how far away is it from 0? 1. So I had the ordered pair 1, 1. And then finally, I got the absolute value of 2. How far away is 2 from 0? It's 2, okay? So I get this ordered pair of 2, 2. Okay, so these are all ordered pairs in the table. Negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 2. And I can put these all on the graph. Okay, so I'll start with negative 2, 2. So that'd be negative 2, 2. Try to use a more prominent color here, but negative 2, 2 is right here. Then we have negative 1, 1, which is here. Then 0, 0, which is right here at the origin. And then 1, 1 here, and then 2, 2 right there, okay? Now what happens here, just with this, the little amount of graph that we have, we can see that the line goes down. Now look, it's straight between these first 3 points, okay? But then it breaks the other direction, and even though it's a straight line in the other direction, it's not a straight line through the whole thing, which again, by the graph would tell us this is not linear. If we wanted to show this with the table, then we would use the slope on that one. And I would say, look, right here, again, as a ratio, you're looking at y's over x's, so that from 1 to 0, that went down 1. But from negative 1 to 0, that went up 1. Okay, so that's down 1 to the right 1. And then for the next value, see right here, again, we're looking at a ratio, but it goes up 1 now, and then from 0 to 1, it goes to the right 1. That's 1 over 1. And these two values here, they're not the same. Okay, so again, through the graph we can tell pretty quick. Through the equation we can tell pretty quick that it's not linear, but then if we need to tell this through a table, we can tell that pretty quick as well. Now I did skip this first value just to save us some time. This went down 1 and then to the right 1. So we would have had the same ratio for these two. For tables, you should be checking throughout the whole thing. But again, I kind of took a shortcut there to save us some time. Okay, so again, not the same means not linear when those ratios are not the same. Okay, how about this one? Once again, I'm going to go straight to the last question here. They've given us this equation, y equals x to the power of 2. And since it shows me the power of 2 with the x, right off the bat, I know this is not linear. Meaning when I go to my graph, I'm expecting not just a straight line throughout, okay? Well, what about the table on the graph? Would that show us? Well, I'm going to make the table first because that's going to give us some ordered pairs to look at the graph. Okay. So once again, we look at y to the power of 2 here. Y equals x to the power of 2, sorry. Let's come up with some x values to use. I'm going to pretty much use the same values here. Negative 2, negative 1, 0, 1, and 2 right here, okay? Which is going to help me to figure out the corresponding y values here. And just like we saw in that last one, yeah, we got to plug these values into the actual equation to figure these out. So I'm going to say, look, we got this first one, it's negative 2 right there, right? Now that's negative 2 times negative 2, which is 4. You can put that into the calculator, just if you do, make sure you use the parentheses there, okay? So when x is negative 2, I get a y value that's 4. How about when I make the x value negative 1? So that'd be negative 1 times negative 1, which is positive 1. So I got negative 1, 1. And also I got y equals 0 now to the power of 2, which is just 0. So again, that goes through the origin. That's good. And then now we're dealing with some positive values. Y equals 1 to the power of 2. And 1 times 1 is just 1. Okay, so again, that's positive 1. Then we got y equals 2 to the power of 2, which is 2 times 2, that's 4. So in this case, the y value, corresponding y value is 4. All right? So here's all my ordered pairs. We can put these on the graph. Let's go and start with negative 2, 4. So negative 2, 4 would be right here. Then we got negative 1, 1, which is here, and then 0, 0. And just right off the bat here, just with these 3 points, you can see some curvature in the line like this. But further extending this, at 1, 1, we would have this point. So see how it even changed directions, complete opposite directions here. And then we also have 2, 4 as well. Now to expand that table, not that I'm showing, not that I did these values, but you could have said negative 3, 9, and also 3, 9, which would have put us up here. And then we can see a pretty clear change in the changes, okay? So right here we can see that, yeah, these are not very straight line. Not just because I suck at drawing lines, but just because it's curvy, okay? So right here in the graph, we can tell that this is not a straight line, but again, the table would have told us that just between the first 2 points, first 3 points, I should say. So right here, from 4 to 1, that would have went down 3, and then from negative 2 to 1, that would have to the right 1. So as a ratio, that's negative 3 over 1. And then from 1 to 0, that went down 1. So again, as our ratio, we got down 1. Well, from negative 1 to 0, that's to the right 1, okay? But again, these, negative 3, 1 and negative 1, 1, these are not the same. Not the same ratio. And again, with the table, that's why this is nonlinear. Now this one, they gave us this table right here. And now you can make the graph before you make the determination on if this is linear or not. It does say make the equation, so let's see what that would be, okay? Now the first thing I would look for in the equation is the slope, okay? So if we're gonna write the equation, y equals mx plus b, again, I just want to find the slope, and then I'll just put the b value here, okay? So my slope, let's see, this is 8 to 7, that goes down 1, and then the x, negative 2 to 1 is to the right 1. So as a ratio, that's down 1 to the right 1. Let's see if it continues that ratio. So 7 to 5, that goes down 2. Now that's not enough to disqualify this as not linear. We have to look at the ratio of x as well. From negative 1 to 1, that would be to the right 2, which gives us a negative 2 to 2 ratio. These two have exactly the same value if you put these into the calculator, okay? So right now it is linear, but let's look at from 5 to 4, down 1 to the right 1. So that's the same ratio there. And then from 4 to 3, down 1, from 2 to 3 to the right 1. Okay, so down 1 to the right 1. That has the same ratio. And since these are all the same ratio, yeah, this one right off the bat here, we're going to see this one is linear. Okay, that means when I go to the graph here, I'm expecting to see a straight line. Now, what is that ratio reduced? If you did negative 1 divided by 1 or negative 2 divided by 2, you're going to get negative 1 as your slope. That's our slope, negative 1, okay? But what is the y-intercept? Well, the y-intercept, again, let's go back to our y-intercept formula on this one because I'm just going to use the table, although you'll see it on the graph as well. So the y-intercept here. Remember, you can take a y value and subtract the slope times some x value here. And like I said, I just like to use kind of the top one. So right there I can see the top ordered pair there, negative 2, 8. So I can see the y value there is 8. And the x value there is negative 2. And yes, we did find the slope already. That was negative 1. So in my calculator, I put 8 minus negative 1 times negative 2, and I get 6 out of that, okay? So again, that's the ordered pair, though, 0, 6. That's our y-intercept. And again, for the equation, I would just put the 6 right there. But it's positive, so I'll put plus 6. Okay, so now that could be another ordered pair that you can put on the graph, but I'm just going to use the ones that they gave us. So I'm going to start with negative 2, 8. Negative 2, 8, which is right here. In fact, I'll use a different color there. Then they give us negative 1, 7 here. Now we found 0, 6, but let's skip that and show that it would have shown us that. Anyways, 1, 5 here, 2, 4, and then 3, 3 here, okay? So you can see if you were to connect these points like this, it would have went through the point 0, 6 anyways. Okay, but there's the graph from the table, and from the table we were also able to write the equation. So for the table, make the equation and the graph. This one's not too bad because right here we see, again, we're looking at the slope. Y equals mx plus b. Where m is the slope and b is the y-intercept. So let's go ahead and find our slope here. Now, on this one, I can see the y value from 5 to 5, it actually goes up 0, where the x value here is going to go to the right 1. That's a 0 to 1 ratio. And then from the next set, right, this is showing from 5 to 5, that goes up 0. And the x's, negative 1 to 1, that goes to the right 0. That's a 0 to 1 ratio, so that's the same. And so right now it's looking like it's going to be linear, but the next set, from 5 to 5, up 0, 0 to 1, to the right 1. Again, that's a 0 to 1 ratio. And then 5 to 5, that's up 0, and then 1 to 2, again to the right 1. 0 to 1. Once again, we see on these ones, these ratios here are all the same. And since they are all the same, and you have to check all of them, then we know now that this relationship here is a linear relationship, okay? And in fact, if you were to reduce that, 0 divided by 1 is just 0. Yeah, we can put that in as a slope right there, okay? But what is our y-intercept? Let's find out. Oh, I guess this one they gave it to us, 0, 5. So I can see the y value there is plus 5. But again, we're going to see that on the graph, just in case you didn't notice that in the table, okay? So let's put our ordered pairs here on the graph. I got negative 2, 5, negative 1, 5, 0, 5, 1, 5, and 2, 5. And yeah, we can see at this point that it's just a horizontal line right here. Hope you can draw your lines better. But once again, they did show us on this graph the y-intercept right there at 0, 5. So is this linear? Well, if I draw my line a little bit better, you'd see that it's straight, but it's supposed to be straight, okay? So this one also, the graph would have shown you that this is a linear relationship because it's a straight line. Now something else about the equations, which I think hopefully you're noticing on this one. If you can ever write an equation in slope-intercept form like this one, automatically you have a linear relationship. Automatically. If it's y equals mx plus b form, then yeah, you got, remember, for your x's, there's no exponent there. It's not showing the exponent. The x is not in a denominator, anything like that. So right here we can see that it's linear. All right, how about this one? That's 2 to the power of x. And again, we got an x in the exponent right there. So right here, right off the bat, I'm going to say this one's not linear. Okay? So that's enough for me to tell. But it still says to make the table and the graph on this one. So again, let's look at some fairly simple values to use on this side. Let's see, again, negative 2, negative 1, 0, 1, and 2. Okay, so I'm just kind of keeping in there. And while you do have a choice yourself, I know these values should fit on the graph, okay? So for us, we got the equation, y equals 2 to the power of x. And I really do recommend that you just put these into the calculator, but now the x is negative 2 here. If you put that in the calculator, you're going to get 1/4, okay, which is true. In fact, just for the graph, you can even use the decimal value on that if you want. You can access the decimal value by just pushing the double arrow button above the enter button, and it will give you that value. So 0.25 or 1/4. Then y equals 2 now to the power of negative 1. This is going to give you 1/2 or 0.5. So that's my corresponding y value. How about y equals 2 now to the power of 0? Well, that gives us y is 1. Anything to the power of 0 is 1. So 0, 1, that's pretty nice. Y-intercept right there. And then next I got y equals 2 to the power of 1, which is just 2. So 1, 2. And then finally y equals 2 to the power of 2, which is 2 times 2, that's 4. Okay, so 2, 4. Again, there's our table. And you can see through these values, even from 1 to 2, that would be a 1-to-1 ratio in change, and then 2 to 4 is a 2-to-1 ratio. Those are not the same, which again would have told us that is not linear. Well, let's put these points on the graph. Okay, so I got -2 and a fourth, right? I'm gonna put it right there, and then -1 and 0.5 here, and then we have 0, 1, and then 1, 2, and then 2, 4. Yeah, this one, while we're not too concerned about what exactly it's doing, we can see some curviness to this line. Would look something like this, okay? So again, that curvy line right there tells us that this is not linear. But again, the table would have shown us that as well, right? From 1 to 2, you went up 1, to the right 1. So that's a 1-to-1 ratio, and then from 2 to 4, up to the right 1, that's a 2-to-1 ratio. Again, these are not the same. So again, on this one, we can see that the x is in the denominator. So right off the bat here, once again, with the x being in the denominator, this one's not linear. Okay, well, let's go ahead and put some x values in our table. Again, I'm just going to use the same ones. I'm going to say, you know what, actually I'm going to change the values a little bit on this one. And the reason I'm going to do that just because I want whole values. And the only way I'm going to get whole values on this, well, actually I'll get some decimal values, but I want nice ones. So I'm going to use -4, -2, 0. And then also we'll use 2 and 4 on this, okay? All right, so now something interesting will happen on this, okay? But we'll deal with that when we cross that bridge on this table. So here's my equation. I got y equals 2 over x. 2 over x. But I'm saying that the x value here, I'm going to start with -4. There we go. And if you put this in the calculator, you get y equals -1/2. Okay. So again, for the graph, you can say -0.5 if you'd like. Next up, we got y equals 2 over now -2, which is -1. So that's 2, -1. Now, the problem here is when you put 0 in to your calculator. This one, if you put this into the calculator, the calculator is going to tell you it's a divide by 0 error. Or something like that, okay? So what this tells us then is that we just can't use this value. It's undefined, okay? So we can't even use this value in there. And that should tell you something about the linearity of this function or equation. So now we got y equals 2 over, now it's just 2, which is y equals 1. There's a 1, 2, 1. And then finally y equals 2 over now 4. But this one's going to be +1/2 or 0.5. So now that we got that, let's go ahead and put this into the graph right there. So I'm going to start with the point -4 and then -0.5. So that's going to be -4, -0.5, about right here. And we can do -2, -1, about right there. And then we also have the point 21, right here. And then the point 4 and 0.5. So 4 and 0.5, about right there, okay? Now, the problem with this, you can see, I mean, even if you went in here to try to connect the points, you're not going to get very far. It definitely is not a straight line, even if you just went from left to right, which you wouldn't do. But we're not concerned with how this graph will look completely. We just need to understand that this is definitely not a linear relationship. So that brings us to the objective then. I can determine the independent and dependent variables in a relationship, and also I can determine when a function or equation is linear or non-linear.